So what I was saying that if someone asks me that I need to calculate this probability that capital X takes values from mu minus sigma to mu plus sigma, how am I getting these values? This is the main important question that I was discussing in the previous session. The way that has been performed is the following. We are going to find this definite integration from mu minus sigma to mu plus sigma. We are going to integrate the probability fx with respect to x, where fx x is given by this expression 1 by sigma root 2 pi e to the power minus half x minus mu by sigma whole square. Or if you want to look at it in terms of the standard normal variable, so you can say that this is nothing but the integration from minus 1 to plus 1 fz small z dz, where you know that fz small z dz is fz is actually 1 by root over 1 upon root over 2 pi e to the power minus half z square. Now both these expressions are actually very difficult. Analytically, these probabilities, if you want to find the probabilities, these are very difficult. You have to do lots of substitutions, and it actually takes lots of amount of time and energy. So one easy process to do these calculations is to do it by numerical integration. Numerical integration. I do not know whether you have numerical analysis in your electronics and communication engineering courses, but there are several numerical integration process. Let me name a few. Say, for example, one numerical integration process which is called trapezoidal rule. Another numerical integration process that you can perform is Simpson's one-third rule. One-third rule. Another numerical integration process that you want to perform, you can perform over here is Simpson's three-fourth rule. Another numerical integration that you can perform is the Wedel's rule. All these rules are actually numerical integration process. When we apply the numerical integration, when it is not possible for us to calculate the things analytically, we go for numerical process. So these are the methods by which these probabilities can easily be calculated. And not only this, in nowadays online, these ready-made C programmings for online C programmings for this particular methodologies are available. Okay, so you can do two things. You can go to any online site where the program of this trapezoidal rule and Simpson's one-third rule is written. Just put the limits -1 and +1 over here, give the expression of the function, and you will see that the probability will be calculated instantly. Or you can grab the algorithm of the program, you can copy it, you can apply code blocks, or you can open Turbo C++. You can go to those portals. Now copy paste your algo over here, try to run it. Okay, get rid of the errors, and once the program runs, you will see that you will be getting the programs for this numerical integration process, and with the help of these numerical integrations, you will be able to calculate these probabilities. So these two things that you can perform. But if you are thinking at this point that you need to do this kind of calculus in this particular course, the answer is no. You don't have to perform this particular problems, integrations over here. Numerical integration is not the topic of our discussion. And to ease the situation, I asked in the previous session to memorize those probabilities, because in statistics, when we apply probability law, nobody actually does this kind of numerical integration process to calculate the probabilities again and again, because these are known. These have already been calculated. So this is the answer to the question. That's why you are supposed to remember this. Another vital question that one can ask me at this point is the following. One can ask me, okay, we have got 7 to 8 area properties that we have to perform, we have to memorize. Now, what about, suppose we have got some range like the capital Z is going to have some kind of value from say minus 0.39 to plus 0.39, an arbitrary value. This situation may also happen. This situation may also happen, but in my area property, this is not reflected. So what we can do over here, then also you don't have to worry about it. Either you can do some sort of manipulation to bring this particular form into in a certain way so that you can apply the area property, or you can do one another thing that I'm going to show you by the presentation. So I'm stopping the share of the whiteboard now, and I'm going to present this particular page. Just look at it. I hope you are able to, you actually can see the table that I'm presenting to you. This is the table for the standard normal probabilities. And you see what is the meaning of this. This meaning of this probability is the following. The meaning of this probability is the following. So we have this probability of Z less than X. Probability of Z less than X. What I was asking you, suppose in some problem, you are actually supposed to find this quantity, minus 0.39 to plus 0.39. So how can you calculate this probability? Because it is not, area property will not help you in this regard. So what we can do is the following. What is the, it's not, just a minute. So just let me scroll a bit up in the table, and you find that meaning of this particular table is the following. This is the meaning. And suppose with respect to this, I have to mark this point, 0.3 over here. These are the values of X, as you can see. And if I move on to the right hand side, you just come to this particular point, 0.09. Because if we add 0.3 to 0.09, what we get 0.39, isn't it? So if I look at this value, just carefully observe. If I look at this value, 0.6517, what it actually means with respect to the meaning of this particular standard normal table, it means that probability here small x is equal to 0.39. So it means that probability that capital Z less than 0.39, this probability is actually equal to 0.6517. This is the meaning of this probability. This is 0.6517. So this is given to you. Now, how to use this particular thing over here? Let me talk about this. If I try to expand probability of Z less than 0.39, it actually means that there is no lower bound, as you can see. So you can write this particular probability as the following. In the lower limit, you can write minus infinity, and in the upper limit, it is bounded by this particular point, 0.39. So this is given to you, which is 0.6517. Okay, approximately 0.65. Now, if I draw the normal curve, like this, if I draw the normal curve and not the normal curve, rather the standard normal curve, now you are going to see why it is easy to apply standard normal curve than to apply normal curve, because this particular point has now become origin, and left hand side is the negative portion and the right hand side is the positive portion, and it is running from minus infinity to plus infinity. Now my upper limit is 0.39, so I can roughly consider a point Z equal to 0.39 over here. So this is my 0.39. Suppose this is my 0.39. So according to what we have written over here, we have actually found, we know that the area of this portion is actually given to us. Area of this portion is actually given to us. This is the thing that have been given to us. Now what we actually need, we need this probability. This probability. So you know that this point z equal to 0.39, you can imagine, you can consider a point z equal to minus 0.39 on the left hand side, which is equidistant from z equal to 0. Okay, so you can imagine a point is lying over here, which is equidistant from z equal to 0. And the blue colored portion is the probability that that is known to you, which is 0.65. Okay, so first of all, I will try to find out the probability of this portion. I will try to find out the probability of this portion. So I'm marking it. This is the region, this is the area that I'm going to find out. Now you see that if one tries to find out the probability that z lies between 0 to 0.39, if I want to find it, what I can do, I can write it as, in terms of a difference of two probabilities. I can subtract from this probability minus infinity to 0.39. That means the entire blue portion. I can subtract this portion that I'm going to mark with pink color. This particular area that I'm marking with pink color, that I'm going to subtract. So I can subtract this area. I can subtract this area, this pink colored portion, from this yellow colored portion. Not from this yellow colored portion, from the blue colored portion. That means the entire part. It would be nice if I used to write it in blue color. Then you will be able to understand it. So this is the entire area that is obtained from the table. From this blue colored portion, I'm going to subtract the pink colored portion so that I get the yellow colored portion. So if I do so, then we'll be able to calculate the yellow colored portion probability. Now, what is the yellow colored portion probability? So I'm writing over here. This part, you just carefully, attentively listen to me. This part is very important and it is required in every calculation. Now, you see that this blue colored portion, the probability is known to me. This probability is 0.6571. It is coming from the table. But what about this yellow colored portion? Sorry, this pink colored portion. The pink colored portion contains the, as you know, the normal curve is symmetric. The pink colored portion contains the 50% of the total data. And the right hand side from 0 to infinity also contains the 50% of the total data. So from the probability that z lies lying between minus infinity to 0, this probability is actually 0.5. Let me write it in blue color, 0.6571. And let me write this probability in pink color, which is 0.5. So what we have got, you can subtract the two probabilities. Let me subtract it quickly with my calculator. Just a minute. So it is coming as 0.657.5, which is 0.1571. So this probability that is coming is 1.1571. 0.1571. So this probability, you see, this is the probability of which portion? This is the probability of this portion. This is the probability of this portion. Okay. Now, but we are interested in finding this probability. This is the thing that we were interested in finding. But as you know that normal curve is symmetric about z equal to 0, and 0.39 and minus 0.39 are equidistant from z equal to 0. So this particular expression that I have ticked over here, it can be written as twice probability z lying between 0 and 0.39. Why? Because this portion and this portion will have equal probability, because z, capital Z, is a symmetric curve. So what you need to do, you need to take twice of this probability that you have calculated, twice 0.1571. And if you do this calculation, you'll see that the probability will come out to be 0.3142. So this is your answer. This is the answer to the given problem, simple problem that I have done over here. My objective is to show you how to take the help of the area property or the property of the normal curve, or we can take the help from the table to calculate various probabilities with respect to a given problem. So you see, in this particular problem, the question of doing calculation with the help of calculus or integration, it is not coming into the picture. The thing that I was discussing was just for understanding that what is happening. Now, when you will do the probability questions, I mean, when you will be doing the problems of normal probability law, you don't have to perform any calculus over here. Everything has been done and has been made ready-made for you. You have to just go and pick whichever is necessary for you. I am recording this particular session. If anybody has not understood any part of this particular portion, then you don't have to worry, because you are getting all my recordings in the YouTube. And the thing that I'm not liking, because I'm saying it to you, only 28 participants are actually doing the class. Others are not doing. If they think that they will get the record later and they will see it, then why to attend my class at all? Why to see my recording at all? Many other good lecture videos of on normal probability law are there, so they can see the lecture videos over there. Okay, so no need to see my video then. I am sending you video, the basic objective that for which I am actually uploading the video, so that if you miss, since we are doing it online, and if you miss any point during the examination you are practicing, and if you missed any point, then you can revisit my lecture and you can see that what I actually told. Okay, so that is the objective for which I'm actually sharing my videos. Now, Lohit Kumar Biswas, you have written 1517 in the chat box. Right, you are, but you have done a silly mistake. Don't do this kind of silly mistakes in the examination paper. It is 0.1517. Okay. Now, this is the thing by which we can do the calculations of probabilities by taking the help of the properties that we have discussed so far. Here we have not taken the use of the we have not taken the help of the area property. The 8 area properties that I have written, I have not taken the help of it. Rather, I have taken the help of this table, and I have taken the help of the properties of the normal curve. Now, if during the problem, if you find something like, say, for example, you suppose in a particular problem, you are supposed to calculate probability of 0 less than capital Z less than 1, then you don't have to come to table to look at it, because you know that probability of -1 to Z to 1, this probability is actually given by 0.6826. Okay, and if you take the half of it, you will get this probability. So here you can apply the area property directly. You don't have to come to the table. So it depends upon the situation. It depends upon the situation, and according to the situation, we are going to choose our process, whether to write it directly from the area properties or whether to take help from the probability chart. This is called the normal distribution chart, and when I'll be sharing the note with you, I will share the chart with you also. So don't worry about it. In different books, the charts are given in different forms. Okay, in this book that I'm actually following, the chart is given in this particular way. So before you apply the chart, you need to see, oh, this particular point is very important. Suppose you have grabbed a book. I don't know what book you have been given from the college library. Whatever it is, suppose you have grabbed the statistics book and you are doing normal distribution problem from the exercise, and you need to take the example, you need to take the help of the normal curve. Then just look at it. What is the meaning of the chart? If you do not know the meaning of the chart, and if you directly apply the probability law, if you directly apply the probability, then it might be wrong. So just you take the help of the, just you see what sort of table is given over here, and by looking at the meaning of the table, you try to calculate the probability. Okay, so remember, in different books, different tables are given in different ways, in different forms. First, grab the meaning of the table and then apply it. Now, let's come back. Now, as I discussed the normal, one important thing that I actually missed in the earlier session was to talk about the following. Suppose this is the normal curve. My drawing is horrible. Don't look at it. This is the normal curve I am drawing, which is x equal to mu. And this point is plus infinity, and this point is at minus infinity. Or if you draw a standard normal curve where the range is from minus infinity to plus infinity, capital Z equal to 0 is the mean. Now it is always, you have to remember always that this curve will never touch the Z axis, the horizontal axis, be it Z or be it X. It will never touch the axis at finite points. Rather, the curve will touch the axis, horizontal axis, at two different infinite points. One is plus infinity or at minus infinity. Okay, so in this, with respect to this, the horizontal axis is actually the tangent to the curve. Horizontal axis is the tangent to the curve, and this, since this tangent is touching the curve at minus infinity to plus infinity, such a tangent is actually called asymptote. Probably you have seen this word asymptote in your school days, and in school I also found that in some books of differential calculus, the probability curve is also given to us for the study. So asymptote is the tangent, is a type of tangent which touches the curve at infinity, either at minus infinity or at plus infinity. And if I talk about the probability function fxx and fzz, if I talk about the probability function, you can also calculate the maximum value. So if someone asks you what is the mode of this particular curve, the mode is x equal to mu. And what is the model value that you can calculate over here? Model value means the maximum probability at the point x equal to mu. So with respect to the normal probability, the maximum value is occurring at x equal to mu. So it would be, so this particular thing, that is fxx maximum, that would be 1 upon sigma root 2 pi, simply this, because you will put x equal to mu and e to the power 0 will become 1. And if it is standard normal variable, then the maximum value will occur at z equal to 0, and the maximum value will be 1 upon root over twice pi. So these two values are actually called the model value with respect to x, with respect to z. So this thing, sometimes it is also asked during the examination. So you have to remember this also. Now, after all these area properties, I am going to show you a problem which you can try by yourself. So for example, I'm considering this problem. Uh, question: the mean yield for 1 acre plot is 662 kilos with a standard deviation of 32 kilos. So this information is given to us. Assuming normal distribution, how many 1 acre plot, in a batch of 1,000 plots would you expect to have yield number 1 over 700 kilos, number 2 below 650 kilos, and number 3, what is the lowest yield, of the best 100 plots, So this is the question. The important part of this particular question is that this assumption that they are making. They're making that assumption that if your distribution is behaving normally, then what will be these probabilities? Now, how these assumptions are made? These assumptions are made on the basis of the previous experiences, past experiences. So if this is the scenario, here I'm not going to talk about how this is done. I mean, how these assumptions are actually done, because these assumptions have been done somehow in some way that I did not discuss it right now. But here I'm going to show you the technicality of the problem, that how to deal with this particular problem with the theory that we have learned just now. Since it has been already assumed that the variable under consideration is normal, first of all, you have to define the random variable that will play an important role over here. So if your random variable is being denoted by capital X, then it will be giving you the yield in kilos for 1 acre plot. This will be the meaning of the random variable over here, because I told you several times that whenever you'll be doing problems on probabilities, first of all, you would make sure that what random variable you are playing with. And it is also given that capital X is following normal distribution, that I'm going to write it in the following manner, with mean mu and variance sigma square, where or standard, or you can write that capital X is following normal distribution with mean mu and standard deviation sigma, where mu is 662 kilos, and standard deviation sigma is 32 kilos. Okay. What we need to find is the following. Number one, we need to find what is the probability that the yield is greater than 700 kilos. So we need to find probability that X greater than 700. To calculate the probability, we need to transform the random variable capital X to the random standard normal random variable capital Z. For this transformation, we are going to apply the transformation law that we have discussed over here. Here we know that capital Z will be X minus mu by sigma, and but here mu is 662 and sigma is 32. Okay, this is the thing that that will be uh, playing important role over here. So we need to subtract the mean 662 from both the sides, and we have to divide it by the standard deviation, that is 32. And automatically the left hand side of this will become capital Z by definition, and right hand side will become something. Let me calculate it. It will become 700 minus 662, 38 divided by 32, which is approximately 1.19. So we need to calculate this particular probability by using the normal probability law, a normal probability chart. But for this, every time you do a particular problem on normal probability distribution, you need to draw the normal curve. Since you are sitting for the online examination, so probably this requirement is not there. You don't have to draw anything. But if you are sitting for offline examination, every time you do some normal distribution problem, you have to, for each case, you have to draw the normal curve. Now, now, since we are interested in this particular point, so we shall mark the point somewhere on the right hand side, because this point is positive. So it is 1.19. This is the point that we are marking over here. And according to the problem, we are interested in finding this probability. Okay. But we have to take the help of the normal curve. And we know that from our previous chart that I actually shared with you, we know these values are given. This sort of values are given in my chart that I am following from the book. That means probably we know this value. If I take X equal to 1.19, we can get the probability from the normal chart. So I'm not resharing it. Let me see the value from the normal chart. So if I look at the value, it is just a minute. Okay, I'm not able to find it. Let me stop the share and let me. Okay, it is there. Just a minute. 1.19 means that means this is 1.1 and this column is 0.9 column, 0.09 column. So 1.19 means 1.1 plus 0.09. Okay, and probability of Z less than 1.19 is actually given by 0.8830 from this particular chart. 0.8830 is the probability. 0.8830 is the probability. Okay, and so let me stop the share. 0.8830. Just I have to remember it. Okay, so this probability is 0.8830 from the normal table. So this region is known to me. We know that probability that z lying between minus infinity to 1.19, this probability is given by 0.8830. Now we are interested in finding this probability. So how can I do it? Let us try to find, first of all, the probability of this region. Now, probability that capital Z lies between 0 and 1.19 in the previous, by the previous process, we can calculate it as follows. We can subtract from this probability this region. And if I do this calculation, we know that this particular region is 0.5. So 0.8830 minus 0.5 will give you 0.3830. This is the probability that we are calculating from here. So this particular part is 0.3830. Now you know that this entire half is having probability 0.5, isn't it? So we can subtract from 0.5 this quantity 0.3830. And if I subtract it from 0.5, the probability will be coming as 0.117 approximately. So this is the probability that in 1 acre plot, one acre plot, the yield will be greater than 700. Okay, so my ultimate answer will be in a batch of 1,000 1 acre plots, the yield over 700 kilos, the expected number of yield, over 700 kilos will be 1,000 multiplied by this probability, which is 0.117, which is 117. So in 117 1 acre plots, if you have 1,000 plots, then you will be able to see that in 117 1 acre plots, the yield will be more than 700 kilos. So this is the way by which we can take the help of the normal curve. Now I am leaving this problem and this problem for you to do by yourself. Try to solve this particular problem and this particular problem. Just think of it. You can take the help of any book also. Try to do it, and if you are not able to do, then I can discuss it in the next class. Or you can ask me, I will give you the solution. So with this, I'm going to conclude my today's session. Hope you have enjoyed and thank you for joining. See you in the next class. Till then, bye.